Our project is about removing oil from water using a process called electrocoagulation. Oil contamination of stormwater and sewer systems is an ongoing problem. Contaminated water presents health issues for the community. Electrocoagulation is a promising way to remove that oil, but it's not fully tested at a small scale. We wanted to see how well it works in a simple lab setup using affordable materials. This is to help us identify parameters that can make the process scalable and cost-efficient. Our experiment directly addresses the need for a low-cost, effective method to treat oil-contaminated water. By using readily available materials, we are able to see how electrocoagulation can treat oil-contaminated water in a household setting. In these cases, the oil is usually emulsified, meaning tiny oil droplets are spread out and suspended in the water. Electrocoagulation works best for this kind of mixture and could be a low-cost solution for areas with limited resources. First, we made our oil-water mix using 500 milliliters of distilled water, 2.5 milliliters of oil, and a gram of salt for conductivity. We stirred it well to get an emulsified mixture, then we placed aluminum or steel electrodes 2.5 centimeters apart and applied 12 volts DC. The anode will release metal ions which neutralize the oil droplets so they clump together. These ions also form flocks that trap even more oil. Meanwhile, hydrogen bubbles at the cathode will lift these flocks up to the surface, forming an oily foam we can skim off. Any leftover sludge settles and can be filtered out.
In our first couple trial runs, we were using a 2-liter tank. Pretty quickly, we realized that the tank, especially the width, was just too big for the power supply we were using. The oil kept resurfacing without forming foam or flocks, and basically nothing was getting removed. So we made a switch to a smaller setup, a 500 milliliter jar, and once we did that, things started working. We started seeing actual flocculation and way better results overall. We ended up running 5 experiments to test 2 main variables, the types of electrodes and the type of oil contaminant. In experiment 1 through 3, we focused on changing the electrode combination using aluminum and steel in different pairings. We tested used motor oil for all 3 since its darker color made it easier to observe the changes. And after seeing that the aluminum setup gave us the best results, we stuck with that pairing for experiments 4 and 5 and shifted our focus to the oil type. We then tested new motor oil and canola oil in the final 2 experiments. In experiment 1, we used steel as the cathode and aluminum as the anode. This experiment had to be run the longest and it did remove the oil pretty well, but flocks didn't form in a way we could scoop them up, so we had to rely on filtration. The water did end up being decently clean, but in experiment 2 we made both the electrodes steel, which made the flocks form extremely fast, so we only had a runtime of 15 minutes. Even though flocks were solid and easy to remove, they were quickly breaking apart and mixing back into the water, so the result wasn't as clean and still had slight oil contamination. In experiment 3, we now made both the electrodes aluminum. This gave us the strongest performance overall, as the flocks were consistent, stable, and the water looked the clearest. Since the double aluminum electrode setup worked so well, we ran 2 more experiments using it, this time by changing the oil types. These are the time lapses of our experiment, where on the left you can see the used motor oil, the middle is the canola oil, and the right is the new motor oil. All 3 of these runs gave great results with very similar levels of removal, and generally, all the results from this section were really consistent. Each test produced very clear water and strong visible flocks, making the aluminum setup a solid choice across different oil types. This is likely because aluminum releases Al3+ ions, which form sticky lightweight flocks, and using the same metal helps keep the reaction way more balanced.
During electrocoagulation, oil droplets aggregate with the hydroxide flocks to form larger, denser particles. These flocks behave like suspended particles subject to gravitational settling as described in Stokes' law. The size, density, and shape of these flocks directly influence how fast they settle. In our model, Stokes' law computed the settling velocity of aggregates, while the beta equation determined the collision frequency between particles. Settling velocity and collision frequency determined whether flocks formed, and a Monte Carlo simulation provided probabilistic estimates of flock formation success by randomly sampling values from fluid density, aggregate size, and shear rate parameters in the model. Electrocoagulation is very effective for removing oil from water and should be evaluated further on a larger scale. A future change would be to let the system settle after flocks have formed. This would provide insights into settling behavior that could be modeled using Stokes' law. Another change would look at how low the voltage can be for this process to still work.